Welcome back to Physical Science Live, Week 3. I'm Mr. Putnam. Last week we looked at the structure of the atom, and we kind of considered why we can't really see an atom, and even if you could zoom in close on one, you still couldn't actually see it. Well, this week we're going to explore that structure a little more and kind of find out how we discovered the structure of the atom, even though we couldn't see it. And we're also going to consider the periodic table and how the structure of the atom relates to the atom's position on the periodic table, how we organize elements or atoms in the periodic table. So I want you to look at this image here. You can see three elements, lithium, sodium, and potassium, all being dropped into water. And you can see they react with the water. So based on what you see here, would you expect rubidium or cesium to be more or less reactive than these? Now, of course, you might have no idea until you take a look at the periodic table. So the three elements that we're dealing with are lithium, sodium, and potassium that are in here. Potassium is K. Now the first question I'd like you to ask, and this is actually your first lecture question before the one I had up on the page there, which of these three elements looks the most reactive to you? Which appears to be reacting with the water the most? That's your first lecture question. Your second lecture question is, based on that, this is lithium here, sodium here, potassium here. If you consider the trends in the periodic table, would you expect the next two, moving down in this direction, to be more reactive or less reactive? That's rubidium and cesium, Rb and Cs. So your second lecture question is, would you expect rubidium and cesium to be more or less reactive than potassium, sodium, and lithium? And to answer that question, I will give you yet another video. This is rubidium being dropped into water. Now you see a person wasn't even bold enough to actually hold that and throw it in the water themselves. They set up some contraption with which to do that. So you can assume there's a little bit of danger, probably a bit more danger than before. You can see this is a little more explosive than the last version. So that should answer kind of that second question for you. Potassium, I thought, seemed the most reactive, and you can see when you look, you'd expect maybe rubidium and cesium to continue being more reactive as you move down the line. Well, let's take a look at cesium. Are you excited? I know I am. When you dump cesium in water, you can see it just explodes dramatically, the glass pitcher that the cesium is dropped in. So these elements get more and more reactive as you throw them in water. Now you might be a little surprised, thinking, sodium? I put sodium in water all the time, right? Sodium and chloride. Well, the chloride, or the chlorine, which is also very toxic, serves to actually neutralize sodium. So when you eat table salt, which is sodium chloride, together, the sodium is neutralized by the chlorine, and we'll see why that works in just a second. So let's consider why, first of all, these elements react in water, and second of all, why they seem to get more reactive as you move down the alkali metals in the periodic table. So here is an atom of lithium. You can see the electron configuration here. Here's an atom of sodium. You see there's more electrons, of course. We have more protons. Lithium only has 3 protons, 3. Sodium has 11 protons, which you can see there, big 11, atomic number. But you can see with the electron configuration, there's one similarity between these two. What is similar? You can see they have shells of electrons, an inner shell, then a second shell. This one has 3 shells of electrons. What's similar about the outer shell of electrons? This will be your third lecture question. What is similar about the outer shell of electrons? Well, I'll tell you what's similar. What's similar is, if you haven't figured it out already, they both have 1 electron in the outer shell, right? Well, let's think about the structure of an atom for a second. We know we have these protons and neutrons in the middle, right? And the protons have positive charges. And in the middle of the nucleus of an atom, if you've got a bunch of positive charges, first of all, you'd be a little shocked that those like charges aren't repelling each other, right? Don't like charges always repel? If you have positive charges together, don't they push each other apart? Well, we were shocked at that too when we discovered what was going on inside of an atom, and so we realized there must be some other force that we don't even know about inside the atom that's holding them together. Well, it's mediated by the neutrons, and we call it the strong nuclear force. Because basically all we knew about it was that it was a force that was strong, because it was able to hold those charges together, those protons, and it was in the nucleus of the atom. We didn't seem to see it anywhere else. Then the next thing you'll notice about an atom, besides the positively charged nucleus, is that these electrons are negatively charged, and you can imagine that they are somewhat attracted to the nucleus. In fact, the positively charged proton helps to keep these electrons nearby. But not too nearby, you see, because the electrons are repulsed by each other, and they don't have a strong nuclear force to hold them together, or it doesn't act over those distances. So these electrons in the atom are repulsed somewhat by each other, so they get into these shells where they kind of find a relationship where they're attracted to the center, but they're kind of far enough away from each other to feel comfortable in terms of those forces. So these forces kind of balance to hold the electrons in a certain place. They're held close by the protons, but they're held a little bit at a distance by their mutual disdain or repelling of each other. So that's the structure of these things, and it's kind of similar, to positively charged wall and a negatively charged balloon after you rub it on your hair, right? And they'll stick together. Or if you have two balloons that you've rubbed on your hair, they'll repel each other because of those like charges. I'm just letting you know that these same charges that affect an atom on this small, tiny atomic scale also are the same forces at work on a large scale. Well, let's look at the rest of the atoms now. We can see now potassium, atomic number 19. Again, one electron in the outer shell, right? Then rubidium and cesium, all having that one electron in the outer shell. Now look at the second shell, the second most outer shell, the second outermost, the second shell from the outside. How many electrons are in that second outermost shell? Now don't count lithium here, but counting all the rest of these, sodium, potassium, rubidium, and cesium, how many electrons are in the second shell? That's your fourth lecture question, and if you answered 8, then you are correct. But just leave the answer down, whatever you had. It's okay if you got it wrong. I just want you to participate. 8 electrons. Well, 8 seems to be a really stable number with most atoms of most size, not these tiny ones, but of most atoms of most size. And it's a stable number for kind of holding electrons in close to an atom's nucleus, but far enough away from each other. But when you add another electron beyond wherever you have this sort of stable outer shell of 8, it kind of expands the size of the atom because it doesn't have room to fit a 9th one in there very well. So it expands it out and puts it in what we consider another shell. But it basically just has to move out of the way because there's just not enough room in there. So it still has some attraction for the center, but it also is kind of a little more on the outer part of the atom. And the reason I'm telling you this is because it kind of explains why, first of all, these atoms are explosive in water, and second of all, why they get more explosive as they get bigger, as the atoms get bigger. So the reason they're explosive is because the atom feels really stable with those 8 electrons. When it gets another one, that electron in the outer shell is really, not as attracted to the middle as these other ones. Much more easily lost. In fact, it almost wants to get away from all these other electrons that are inside of it. And it can do that under certain circumstances. In water, it's easy for electrons to travel, and they can be attracted to ionized parts of the water and things like that. And so those electrons become free to go. Now, with a small atom like sodium, say, those electrons are free to go, but they're still fairly well attracted to these protons in the middle because they're still pretty close. But when these atoms get so big with their electron shells, atoms like cesium, this electron has such a weak attraction for this inner proton and is so anxious to get away from all these other electrons that are sort of in its way or repelling it, that it much more easily gets lost and it much more instantaneously will find a way out if it gets an option. And when it gets put in water, it does get that option to leave. Basically gets a better offer, like it's on a date, and then it sees someone like that he'd rather be on a date with and says, I'm leaving, I'm going home with this person or whatever, I don't So the electron is much more anxious to leave, and that's what makes it more explosive, because those electrons leave en masse, however you say that in French, much more quickly, and they can be much more explosive. So you can see then kind of how this works, and this all takes place with these alkali metals in this one group. So every time you have a full outer shell of electrons, which is 8, and then you add another proton and another electron to get to the next elements in this row here, and you're going to end up with an explosive or potentially explosive reactive type of an element. All right. This is about your participation. These are the state standards. This is what the state wants you to know about science. Specifically today, we're going to focus on these two, explaining how atomic structure is related to the properties of the elements and their position on the periodic table. We already saw that. So the state's going to be really happy if you can remember that the structure of these electrons around the outside relates to the similarities between elements that are in the same row on the periodic table. So elements that are very reactive might be over on the left side where they have one extra electron. All those elements are going to have one extra electron in their outer or valence shell. We're going to learn all about that in the electron section coming up. And then we're also going to look now at an example from history, the history of science, that illustrates the modification of scientific knowledge in light of challenges to prevailing explanations. And we're going to do that with a firearm. This is a bug assault rifle. We're going to consider now using this bug assault rifle as my alpha ray shooter gun, whatever. Why we overturned this model of the plum pudding model of the atom. We used to think the atom was like a plum pudding because all we knew about it was it had these electrons that would sometimes come out of it, and we assumed they must have been sort of statically stuck in there like raisins in raisin bread until they were liberated by some sort of chemical event or something like that. Well, I asked you recently what could you do to plum pudding in order to make it deflect bullets, and I want to illustrate what we realized when Ernst Rutherford shined his pointed his alpha ray gun at some gold foil and discovered that, shockingly to him, some of the particles, or alpha particles, bounced back or were deflected by the gold foil. Now, gold foil is unique. It can actually be made incredibly thin, less than half a micron in diameter, a micrometer, which means a sheet of paper is about 50 microns thick, so you can fit more than 100 sheets of gold foil in the thickness of one piece of paper. So it can be very thin, but even if it's that thin, the thickness of it is still not like 5 atoms across like this, but the thickness would be like 3,000 atoms across. So if you shoot through gold foil with an alpha particle, some sort of alpha particle gun, it's going to have to go through 3,000 atoms to get from one side to the other to get out the other end. But that didn't seem like a problem before because we assumed that the mass was spread out. We knew about how big the atom was, and we knew how much it weighed. And we assumed that that mass, m over v, was all spread out. So that mass was spread out to take up the whole volume that the atom the structure of the atom seemed to allow it to take up. Well, if it was spread out that much, then things would very easily pass through it, much like how the salt from this bug assault rifle, there's salt in here, you shoot, it's actually a way to kill flies. So you can shoot salt at flies like a shotgun kind of. It sprays the salt at them and kills them. Sorry if that offends you. But in this case, we're not killing any flies, just paper. Hopefully that's okay. And with this bug assault rifle, I'm going to shoot at this piece of paper up here on the wall, this newspaper. You can see I already did this once, actually. And when I do, I'm going to shoot at this house right here. You're going to see a hole created, right? Hopefully you can see that hole. Well, that hole shows that the salt was powerful enough to pass right through that particular piece of newspaper. And that's exactly what would happen with alpha particles if the mass of the atom was all spread out throughout its whole volume. But what Ernst Rutherford discovered when he shot at that gold foil was that some of the particles bounced back. Most of them still went through, but some of the particles bounced back. So the way I want you to think of that, like with this newspaper, is if, for example, I seem to have lost one of my pieces of newspaper, so I'll just use the one on the wall. Imagine that I crumpled up this newspaper into a ball like this, and let's say I hung it up in the same place where that atom was before. But now the paper is all crumpled up in this tiny little ball. So I'll hang it up there. And you can kind of see now that there's still the four corners that we saw before of where this paper was. That's the volume, or that's about how much space was taken up by the atom. But now we're going to assume that the only way that we could get some particles to be deflected is if the actual mass was all crumpled up in the middle or in some part of the atom. Who knows where, but the middle makes the most sense if you think about the charges associated. And then we're going to shoot our gun again at the wall, and we're going to see that if I shoot, most of the time, my bullets can pass right through without ever hitting anything, right? Just like you would expect. But when I happen to shoot it right at the ball, you can see it hit the ball. It didn't go through the ball. It couldn't go through the ball. But rather, it deflected, and the salt went all over the place. In fact, here's some on the table. Tasty. Well, that's what happened to Ernst Rutherford's alpha ray particles, and that's how he determined that that mass is compacted into a tiny little ball in the middle. It's not all spread out, but it's all compacted in a tiny little ball. Here's Ernst Rutherford, one of New Zealand's most famous sons. New Zealand. He was even on the postage stamp, as you can see. Here's me reminding you, mass divided by volume is density. So hopefully you can do your density gang sign. And another way of thinking about this whole experiment, of course, is if you have a guy holding a whole bunch of cotton candy balls up somewhere, and a girl shoots a rifle or a BB gun right through them, the BB's going to go right through it, right? There's nothing to stop it or slow it down. But if you crunch that cotton candy up into a tiny, very dense ball, then occasionally those BBs might hit that ball and be deflected. That's the same idea that we're kind of getting at here with Rutherford's experiment. And he said, you might think he's kind of a loser, I don't know. But, you know, everyone has the things that excite them. But he said, it was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you had fired a 15-inch shell at a piece of tissue paper. A shell, of course, like a artillery shell. And it came back and hit you. My goodness. By Jove. So that's how we determine that this tiny little ball, in fact, these electrons are like way out of proportion in terms of size, but if the atom takes up this much space, you would have a speck in the middle where all the mass was accumulated. You know, we talked about the football stadium with just a pea in the middle where all the mass that could be anywhere really in that atom is all crunched up in that one spot. All right, so we've determined now, we've looked at the history of science and determined how scientists figured, even though they couldn't see it, like we learned last week, they couldn't zoom in and actually see what the atom looked like. They determined what it was made of by investigating with an alpha ray gun. And here's sort of an example of it hitting these alpha rays being deflected as they're closer and closer to the nucleus of the gold atom. Or, if you like to think about bullets more, imagine a bullet could pass through the atom at any other place, but if it smashes right into that central place, it might get stopped or deflected. All right, so next week, we're going to look at what happens, you may have already started looking at this, when the atoms in your finger touch something else, like for example my forehead or this person's shirt. If what we know about atoms is that they're not really like solid things, right? They're these waves of sort of electron clouds that are flitting around the outside at like 10% the speed of light. They're going really fast. There's not really a solid outer part of them, right? But everything around us seems to have solid parts. Well, why is that? So what does it mean if this is all made of atoms and my finger's all made of atoms? What does it mean for these two things to actually touch each other? That's something we'll have to investigate next time, and we'll talk more about that. Thank you for being here. For your fifth lecture question, I'd like you to answer that question, actually. You're going to draw a picture of it, but why don't you answer, for your fifth lecture question, what would it look like for an atom in my finger, or what is it looking like right now, if you zoom in close, for an atom in my finger to be touching an atom of this spackling paste. All right. Thanks, guys. See you later.